In this sequence we will look at folding a binary operator over lists. So in the previous sequence I've explained to you how we can use a function defined in the list standard library to map any unary function over a list. When mapping a unary function over a list, in fact all the elements of the list are considered in isolation, which by the way means that this is an operation which is very easy to parallelize and to execute it on several machines independently and to recombine the result. Now, while mapping applies a unary function to all elements of a list, folding combines them using a binary operator. However, things become a little bit more complicated when using a binary operator, since now there are in fact two fundamentally different ways of folding a binary operator over a list. One is called fold left, the other one is fold right, as we will see now on the next slides. Let's first start with the list fold right operation. What this operation does is best explained by the diagram which you see on the bottom of the slide. In fact, here you would use a binary function f, which you apply in an order which one might think naively of being the natural order of function application. Since f would be first applied to the first argument of the list and then to the folding of the operator to the rest of the list. This is called fold right because you can imagine this function application as building up a computation tree which hangs down on the right side of the slide. Now, what would be the type of this function? Well, the alphas would be the element types of our list, and beta would be the result type of function f, which means that fold right would take as first argument in fact the binary function, which would be of type alpha, an element of the list, beta, something which is returned from f itself and gives the result beta, so this would be the functional type. This would be applied to an alpha list, and finally we need also some value which is used at the end, which is always necessary since our folding operation might be applied to an empty list, and what we provide at the end is the result which is returned in case of an application to the empty list. So finally we have a constant which is applied and which is used as the last argument of the applications of f. So for fold right, to understand fold right, just keep this picture in mind to explain what this operation does. Now let's try out our definition of the function fold right, which I have repeated here, and as you can see the type of this function is precisely the same I have explained to you on the previous slide. Now we can use this fold right function and apply it to some interesting functions and lists and see what it gives. So here we have, for instance, fold right applied to a first function which is just the cons operation on lists, an integer list and an empty list, and what we obtain in this case is in fact precisely the same list. Now, to understand why this is the case, please go back to the previous slide and have a look at the picture which I have given to you, which explains in which order the function f is applied to the list, and when you look at this picture you will understand why we obtain precisely the same result for this application. Maybe a more interesting application of list fold right is now folding the plus operation over a list. We would expect this to compute the sum of a list. The last argument which we have to provide is the argument which corresponds to the case of an empty list, and the sum of an empty list of course should be 0, and this is why we have to give here as last argument the value of 0. So if we do this application, we obtain indeed in our case here the sum of the list 1, 2, 3, 4. The same with multiplication. So in case of multiplication, what we should obtain for an empty list is of course the value of 1, and this is why we have to give 1 here as the third argument to this application of fold right, and this allows us to compute here the product of all the elements of the list 1, 2, 3, 4, which is 24. To generalize on the first application of fold right, which I have shown to you, we can now even define the concatenation operation by using fold right. Since all we have to change with respect to the first application of fold right is now to replace in fact the third argument, which was the empty list before, by the list which is appended to the right of the first list. So if we pass this application now to the top level, we see first that the type of this is what we should expect of a concatenation operation. And if we apply this operation now to two lists, we see in fact that what we obtain is precisely what we have expected. In contrast to the folding right operation, the folding left operation has a completely different shape of its computation tree. In fact, as the name indicates, it hangs now to the left. Now let us understand what the type of this function is. Now beta would be the type of the elements of the list and alpha would be the type of the result of function f. As a consequence, what do we get? Well, our function itself would first be applied to an argument which is of the same type as the result of f, that is alpha, then to an element of the list, which is beta, and of course it would return an alpha. So we have for the functional argument a type alpha, arrow beta, arrow alpha. Then we have a type alpha for the constant, which is used in case of the empty list. And finally, we have the list argument, which of course has to be of type beta list. Now let's have a look at the fold left operation, which I have repeated here. So we see in the top level that the type is precisely what I have explained to you on the previous slide. Now let's apply this fold left operation to some arguments. So here we now calculate the sum of a list, but now using fold left instead of fold right. And please note that the order of arguments is now different. This is in fact in order to resemble the computation trees which I have shown to you on the previous slides for fold right and for fold left. So for fold left it has to be in this sense, first the binary operation, then the value which corresponds to the result of the empty list, and finally the list. So when we pass this to the top level, we obtain again the sum of the elements of the list 1, 2, 3, 4. Due to the fact that the fold left operation now applies, that it folds the binary operation in a different order over the list compared to the fold right operation, we can now in fact use the fold left operation in order to define the reversal of a list. Now to do this, we would pass as a function the function which takes a previous result x, an element y, and which returns the list with y put at the head of x. To understand how this works again, please go back to the previous slide, have a look at the diagram which I have shown to you and which explains the order in which the operations are applied. So we might define the reverse operation on lists now in this way, and we can see already that the list is indeed an alpha list to alpha list, and if we apply now this function to a given integer list, we see in fact that it does indeed reverse the order of a list. Now let's see how we can use the folding operations in order to define, for instance, the operation of inner product of two integer vectors. So this equation reminds to you what the inner product of two vectors is in fact, and in order to compute such an inner product, what we have to do is, well, first of all, we compute the pairwise products of the elements of two lists, which would yield a list of integer values, which finally has to be summed up in order to obtain the result. Now, finally, we can put together the map operations, which we have seen, and the folding operations to define in a very elegant and concise way the operation of calculating an inner product of integer vectors. To calculate the inner product of two integer values, we would first use the list.map operation in order to do a pairwise multiplication of the corresponding elements of the two vectors, and then sum up the result using the list_fold_left operation as we have seen on the previous examples. This gives us a definition of the function inner product of two vectors, which is written here, and we see indeed that this is a function which expects two integer lists and which returns an integer list. So let's apply now this function to these two vectors, and we obtain indeed a result 44, and you can very easily verify that this is precisely the result that we should expect. So finally we have here a different application of folding, where we have now a different, maybe a little bit more interesting function which we pass as functional argument. The idea here is now that we would like to count the number of elements which satisfy a certain criterion. And the idea is now that we make the criterion a parameter of this function, which of course would be a functional parameter. So we obtain a function which is called COUNTIF. P would be the criterion, that is a function alpha to bool, and L would be an element, would be a list of elements of which we would like to count the elements satisfying P. Now we can do this using the fold left operation, since the function which we fold now over the list is the function which takes what we have counted so far and the next element of the list, and if the element of the list satisfies the criterion P, then we send the counter +1, and otherwise we send the counter itself. In case of an empty list, of course, we would count 0 elements. So the type of this function would be, of course, well, we have a first argument which is the criterion, that is a function alpha to bool, then we take an alpha list and we send an integer value as the result. For instance, let's apply this function COUNTIF to the function which uses the criterion of being a positive value applied of a mixed list of positive and negative integer values, and when we calculate this application we find indeed that there are precisely 2 values in this list which are strictly positive. As always, you can learn much more about lists and all the functions which are defined in this module. In the OCaml manual, just look into the standard library where you will find the description of the module list.